Welcome back to module 8, where we are discussing light atom interaction, and we have represented so far the classically we have represented light, and we are seeing that when light propagates through the medium, actually certain vector potential is propagating through the medium, and vector potential is nothing but the plane wave, and that's why we call it light is a plane wave. And we have seen the general form of that vector potential which is propagating through the medium, because that vector potential is going to contribute to the interaction potential which will be introduced in the time dependent Schrodinger equation. So we'll take a look at rigorously take a look at the nature of the vector potential. If we are familiar with any wave, plane wave propagating through the medium, it's actually the same as the plane wave propagating through the medium, but just the names, these new terms we are using, these vector potentials. So when I say that light is propagating through the medium, it is actually what is going on. Certain vector potential is propagating through the medium, and it has its maximum amplitude, which is given by A naught, and it is actually varying along this x-axis, and that direction along which vector potential is changing in the medium, it is the direction. This direction is called polarization of light, and this epsilon cap is the unit vector along that polarization direction. So vector potential is changing along this direction, but it's propagating through the medium like this way. So this is the propagation direction. Propagation direction is given by k naught direction. So that's the basic idea. So when light is propagating through the medium, we will visualize as if a certain vector potential is propagating through the medium, and what we have plotted here is the real part of this, which is nothing but A naught is cos omega naught t minus k naught z. We often represent a plane wave with the help of this kind of complex notation, because subsequent mathematics becomes easy to deal with. Otherwise, this complex does not mean anything. We have to convert it to the real part, and the real part is going to be the cos part, which is the cosine wave. So vector potential is nothing but the cosine wave. So light is nothing but a cosine wave, plane wave in one dimensional problem. Now if we look at this, what we see is that everything inside this bracket, this part is called phase of the plane wave, or phase of the light. And what we see here is that here the phase is depicted in terms of rotating dial. So what does it mean? I have this maximum amplitude here, and now it's rotating. Maximum amplitude is becoming 0 because it is aligned on this. Then again maximum amplitude is increasing, going to the maximum in opposite direction. So this phase, at this point phase is 0. At this point, how do I define the phase? Phase is defined in terms of this rotating dial. You can also define in terms of the length. So this linear advancement is represented by this rotating dial form. So at this point, because cos, everything inside this cos function has to be some kind of angle. That's why when it's making a linear transform transition in this xz axis, which is this is the z axis, let's say, along this z axis, when it's making linear transition, when it comes here, it is actually making pi by 2 phase. On the other hand, when it comes here, it making pi phase. When it comes here, it making 3 pi by 2 phase. Similarly here it's making again the it's making basically pi phase, which is nothing but the 0 phase. It is repeating. So what we see here from this rotating dial, this correspondence between the linear motion and the rotational motion, this correspondence suggests that after a certain time the same phase will be repeated. If I am looking at this red color, it will be repeated. If I am looking at this green color, it will be repeated. So the same phase will be repeated, and when the constant phase front repeats, it means that this total part, if I take the time derivative, then this is going to be 0. And if we make it 0, the constant for the constant phase front, for constant phase front, it is 0, which means I have k naught is 0, and dz dt is nothing but the velocity. This is called phase velocity, which is nothing but omega naught by k naught. So phase velocity, we have got the velocity. So we are saying that when light propagates through the medium, in the medium, we don't know what does it mean by light, but in the medium we'll realize that certain vector potential is propagating through the medium, and something is propagating through the medium. It means that it should have a velocity. What is the velocity it has? It has the phase velocity, and this phase velocity is going to be c. This phase velocity is going to be the c in vacuum. Now, and also we see that this phase velocity is positive, which means that this equation is representing the light propagating along the positive z direction, increasing this z direction. There can be another solution for the previous equation, this equation which we pointed out. There is an equation, this equation. We can have another solution, and that solution corresponds to a light propagating along the negative or decreasing z direction. So that is also possible. We are not taking that solution. We are just considering one condition, which is light is propagating along the increasing z direction. And that's why this equation is valid for that particular plane wave. Another concept or idea we should clarify here is that if we have the lambda, which is the wavelength, if I have this z plus lambda advancement, I call it lambda naught, let's say, z plus lambda naught advancement. Lambda is the wavelength of this wave. So if I have z plus lambda advancement, that means I'm going to have 2 pi angular advancement. So this is linear advancement, this is linear advancement, and as a result I will have this angular advancement of 2 pi. Remember, k naught z is representing an angle, but z is representing certain distance, linear. So this part is linear, but total part is an angle, and that's why we added 2 pi advancement. So you see that from here to here, this is called lambda, and this in the linear scale it is lambda, but in the rotational scale it is going to be 2 pi. So 2 pi angular advancement is nothing but lambda naught linear advancement, and if it is so, then I will have this k naught equals 2 pi by lambda naught, and the definition of k naught we get. So in brief, the solution to the combined potential form of the Maxwell's equations in vacuum, which is representing the light, is featuring a plane propagating wave. So light, what is light? Light is a plane propagating wave, and in terms of the vector potential, you can represent it in terms of field as well. and similar conclusions you can make. But we are interested in terms of potential, and that's why we are representing everything in terms of potential here. So in terms of potential, light, what does it mean by light? Light is a plane propagating wave, which is represented by this vector potential of the light, and in the medium it is actually creating this vector potential which is propagating through the medium. It has an angular frequency omega naught. This is the angular frequency, which is nothing but 2 pi nu naught. Nu naught is the optical frequency. K naught is the magnitude of the propagation vector. Magnitude of the propagation vector is the k naught. So propagation vector is this one, along which the here we are assuming that z direction is the propagation vector. So, and magnitude is k naught. A naught is the maximum amplitude of the vector potential. So A naught is the maximum amplitude of the vector potential, and this wave, light wave, propagates with a velocity Vp, which is omega naught by k naught. So Vp equals C, because we are working on vacuum, it is nothing but omega naught by k naught. All these relations we get out of this as a consequence of the plane wave. So similar to the one-dimensional problem, now we have to go back to this three-dimensional issue, and for the three-dimensional problem we get similar results. It can be represented by this way. So previously we have represented a zt equals, this is the polarization unit vector multiplied by a naught maximum amplitude e to the power I omega naught t minus k naught z. That's the way you have represented, and we said that it is actually propagating along the z direction, and a is changing along the x direction, which is perpendicular to the propagation direction. And for the three-dimensional situation, if the position vector is represented by r, then this is going to be the dot product of r. And the real solution, if we find out the real solution, we know that e to the power I theta plus e to the power minus I theta is nothing but cos theta plus I sin theta plus cos theta minus I sin theta. This cancels out, I get 2 cos theta. So cos theta, what is this? Cos theta is nothing but real part of e to the power I theta, which is nothing but half of e to the power I theta plus e to the power minus I theta. So this is what we have used here. If the complex form represented by this, then the real form of the vector potential, which is important, would be represented by this. Cc is representing the complex conjugate of this part. So this e to the power minus I theta is the Cc of this part. That's the way we very conveniently represent. Cc is the complex conjugate of the complex part. So this is what the light look like. I have vacuum, I have light propagating through the medium. It means the vector potential is propagating through the medium, and I have an atom, and this vector potential is going to now interact with this atom in terms of potential. So we are now ready to look at the interaction of an electron. I will first assume, instead of going instead of presenting the light and atom interaction, we will consider that I have an electron, light is propagating through the medium, that's why it has created vector potential, and this vector potential will interact. So with the classical description of light given already, one may write down the Hamiltonian. In the end, always to solve any quantum mechanical problem, I have to get the Hamiltonian associated with this problem. So the Hamiltonian of an electron, which is the electron is assumed to be non-relativistic, which means that its speed or its velocity of electron is much less than C. When this kind of electron, non-relativistic electron, interacting with the light in vacuum, then the Hamiltonian, one can represent the Hamiltonian as this form. Actually, general form of the Hamiltonian for a charged particle. So for a charged particle, with Q charge, the Hamiltonian would be 1 by 2m. M is the mass of the charged particle, then P, that is the momentum operator, plus minus QA plus Q phi. In terms of vector and scalar potentials, one can represent the Hamiltonian, total Hamiltonian. Total Hamiltonian for the interaction, for the charged particle interacting with the light. Now, it is not an easy task to show how this Hamiltonian, how we get this Hamiltonian. We'll just for that we have to know classical mechanics. We have to use classical mechanical equations, Hamilton equation, and we can prove that. But those rigorous methodologies will not use here. We'll just make use of the final form. The final form of a charged particle, we can remember that if a charged particle Q, if a non-relativistic charged particle Q is interacting with light, its vector potential, then the Hamiltonian of the total Hamiltonian would be represented by 1 by 2m, then momentum operator minus QA. That's why A comes into the Hamiltonian, and then phi comes into the Hamiltonian. And for E, because it's an electronic particle, minus E charge, I have now, this is E, and this part becomes negative E, and that's exactly what I have written here. So there is a rigorous mathematical derivation to obtain this kind of Hamiltonian. We'll just use that final result. We'll not show how to get that. One thing is clear here is that Hamiltonian now I have for the charged particle interacting with this, or electron interacting with this electromagnetic field. For that Hamiltonian, I have Hamiltonian depends on its momentum operator. That should be, we know, but in addition to that, it depends on vector potential and scalar potential in the medium, which is originated due to propagation of the light. So one can simplify this equation by writing this as a square. So first we are taking this p square, then we are taking this term, and then we are taking this term. This is just simplifying it. And because we have already said that certain procedure or certain additional condition we'll use to define A. There is an A which is originated due to propagation of light in the medium, but we are going to define A in a certain way. And the gauge condition we have used is that for the Coulomb gauge, we have used A to be divergenceless and phi to be 0. This is the gauge condition we have used. Under this gauge condition, or in other words, following this particular pathway, we try to get the solution. Because if we follow this pathway, then we can get a simplified solution. So definitely phi is 0, which means that this term would be 0 from the Hamiltonian, and then we'll see what is the consequence of this divergenceless A, that we will see. The consequence is following. We will be able to write down this to be minus h car square by 2m